CEA. Mr. Voigt here. This is video 2 of our interior girder beam design. I want to show you. So we had gotten to this point where we had figured our end, well, we figured our loading, which was these 2-point loads of 18,000 pounds, because there's a beam tying in on this side, a beam tying in on the other side, a beam tying in here. Those beams carried 18,000 pounds each, but this only carries half the load of each one of these beams. So it's 9,000 pounds here, 9,000 pounds here, tying to that side of the beam, 9,000 pounds here, and 9,000 pounds here. So together, this 9,000 and this 9,000 are 18,000 pounds of point load. Over here, same thing, evenly spaced. So then we figured using our formulas, our end reactions, and our max moments. And then we used our safety factor to figure out this is going to be what we're designing for. We need to find a beam that will hold this much moment, this much bending resistance. Okay. Then we had to figure out the plastic modulus for a beam this size. So this is what we did here. Now, I did make one error. I want to point this out. I told you to go to the chart, and we chose a 16 by 31 beam, and then we wrote down these values. I'm going to show you real quick what I did wrong. This value right here, I had written this at 12.4. So these are X values. So watch. When I go to my chart, what I had done is I had come here to 1631, and I found my plastic section modulus, which is as close to 48.12 as I could get. And then you also need to write down your I, 375. My I for my x-axis. I had written down the one for my y-axis, my 12.4. Very easy error, but make sure it's your x. I just noticed that somehow and didn't think that was right. So anyway, that's what you need to write down. So now I have all my right, and then I put the D and the TW, if you remember, if we go back here, are the dimensions of this same beam. If I can get down to it. They are this is the web. So the thickness of the web for this beam is 0.275 inches, and the depth, which is the height of the web, is 15.88. Hence the 16-inch height, right? That's darn close to 16. And then so you need those two things to find the area of your web later on. Okay, so here we are. What we need to do now that we've actually chosen a beam, we've chosen a 16 by 31 beam with these attributes. We're going to come over and we are going to check our shear strength. Okay, and if you remember, this is our Vn is greater than or equals to Va omega V. So this is what we're looking for. This is basically our shear strength, right? Our shear strength on each side is 18,000 pounds because we came over here and we said 18,000 pounds for RYA, and 18,000 pounds for RYB. So that's what we get here. This is 18,000. VA, I'm sorry, VN we're still looking for. And we know this. This is our safety factor. For our shear, our safety factor is 1.5. So while we know our load is going to make us hold this much, we're going to design for this much so that we know our beam is plenty strong. Okay, 18. So we need to have 27,000 pounds of shear resistance. So our beam has to be able to hold 27,000 pounds. Okay, so then the next formula, which is Vn equals 0.6 Fy dt to the W. So this is taking the attributes of our beam and making sure that it will hold this much shear. So we know that Vn is 27,000. We know our 0.6. We know Fy is 50,000. I'm sorry, this has to be greater than, and this we don't put this in here. We're looking for this. I apologize. Times our D, which is 15.88, times our TW, which is right here, 0.275. So we multiply these together and we will come up with how much this beam, this is what we need to hold. That's why I can't put that in here. This is what this beam with these attributes will hold. So if we take 50 times 0.6 times 15.88 times 0.275, I think it's 275, equals 131,010 pounds. So we need 27,000 pounds of shear for our beam. It's capable of holding 131,000. So we are good for shear. Our W16 by 31 beam will definitely handle our shear load. Okay, now, so that's good. 8, check deflection limits, or check deflection. And then we're going to go deflection limits. So our dead load plus our live load equals, okay, L over 240. So the length of our interior girder is 20 feet, but it's 20 feet. You got to multiply it by 12 to convert this to inches and then divide by 240. So 20 times 12 divided by 240, and you get 1 inch. So we can have 1 inch deflection with our combined loads. Our live load, on the other hand, is going to be L360, which equals 20 times 12 divided by 360. So we'll just do that, 20 times 12 divided by 360, and we get 0.667 inches of deflection for that. Okay? So, now, check deflection. Okay, so then that's when we bring in our trusty formula sheet. And for this kind of beam, we're going to say, so we're going to say dead load, live load, right? Equals, where are we at? PA divided by 24 EI times 3L squared minus 4A squared. So we're going to have to rewrite this. Now remember, this is the part that gets really goofy. They have to convert units around so that everything cancels out, and what we come up with in the end is inches. So I'm going to go ahead and write this right below it the way that it's going to be worked out on your calculator. So we're going to go here. So our P is 18,000 pounds, right? Our A, and if you look at this diagram, our A is right here. That's 6.67 feet. So 6.67. Okay, but you have to take that feet and convert it to inches. So times it by 12. Okay. And it would actually be 12 inches over 1 foot, and this would be over 1, right? I don't want to get into all of it, but this cancels things out. Because you multiply by 12, it cancels it out. You multiply by 24 times 29 million times 375. And this is inches. This is, I think, what is it, pounds over inches cubed. I mean, and anyway, we're trying to cancel all these things out and end up with inches in the end. And then you multiply this by, you have to go like that, and you go 3, and then you go 20, and again, you got to change this to inches, or to inches, so that's 20 feet, and this is inches over feet, and so go like that, and then you got to square this one. So you got to do all this first, and then you got to subtract 4 that gets multiplied by 6.67 times 12 inches over 1 foot. Okay, so now you got to type all that into a calculator. And I'm going to go ahead and pause this while I do that. And you have to, so you got to be able to do this with all the proper parentheses and so forth. So it'll take me a minute to do this. You should practice doing this. And I'm going to come back with my answer. All right, CEA. I'm back. I did my calculations. So just let me show you how I did this. I wrote all this in here. I had given you this formula before. I actually find it easier to do it in little chunks. I figured this out and wrote it here. I figured this out and wrote it here. Then I subtracted that and came up with a number. And then I did this part right here and put it over this. This comes up with a lot of exponent numbers, so I just leave it in the formula. And then I just put that number in, divide it by, put this parentheses in, type that in. Then I say times this, and it comes out at 0.81 inches. So my total deflection on this beam with this loading is 0.81 inches. And we figured out that I could have, with my live load and dead load combined, I could have up to 1 inch deflection. So this deflection meets our limits. It's underneath 1 inch. So I put live load plus dead load, good. Okay, now if you look up here, our loading, our live load, if we go back to our beginning here, our live load is 2/3 of our load and our dead load is 1/3 of our load. So what they do there now is they give you, instead of making you do this, you could do this whole formula over using live load, just live load numbers. But what you can do is it says live load. Since live load is 2/3 or 0.667 of live load plus dead load, this is the live load plus dead load deflection limit, or deflection is 0.81. I multiply that by my 2/3, and this is now just my live load deflection limit, or my live load deflection, my actual deflection. My limit then is here 1 inch. I take that by 0.667, and this is now my live load deflection limit. So I do the same thing. Since my actual deflection is less than my deflection limit, this beam works. So this is the beam I'm going to use for my interior girders. Okay, so now we've chosen an interior girder and we've chosen our interior beam. So it's a lengthy process, and I'm never going to make you sit down and do this on a test form, but you are going to have to figure this out and be accurate, okay, on your PowerPoint. So I will do one more of these with videos, but then that'll be it. Okay, thanks guys, bye.